Find the maximum value of the function fxy is equal to 4xy, subject to the constraint x squared plus y squared is equal to 8. Now, we don't need this to solve the question, but it is interesting to notice x squared plus y squared equals 8. That's a circle. Okay. X, y, if they satisfy this constraint here, are points on the circle. Okay. And x times y, well, that would be a nice little sort of area for a rectangle, or x times our y. And if we've got 4 of them, we actually make 4 copies of this thing. What we're doing is we're actually finding the largest possible area for a rectangle sitting inside this circle. Now, we don't need to know that, as I already said, to answer the question, but it is useful, I think, sort of conceptually, to realize that there is meaning behind this. There is some geometry going on behind the scenes to a lot of what we see with constrained optimization. Okay? But we're not going to make further reference to this to answer the question. What we're going to do is do constrained optimization, and there's only one way we know how to do that, using Lagrange multipliers. So we'll create a Lagrangian, a function to help us out. So we've got the target function, the objective function that we're trying to, what was it, maximize? Yes, maximize. Okay. And then we introduce a new variable, our Lagrange multiplier. Okay. And then we rewrite our constraint as a function equal to 0. And then we take the part that isn't the equal to 0, and that fits into our Lagrangian, and there we go. There's our function. We use this to maximize or minimize our objective function for xy. Now, how exactly do we do that again? Well, we have to find critical points. Critical points of this function are the only ones that will satisfy our constraint and maximize or minimize our function. Okay, so how do we find critical points? With partial derivatives. Okay, and if you need to, I mean, some people get very comfortable with this. They can start taking partial derivatives in their head. But if you need to, you can, of course, expand this out. And expand the lambda everywhere, just to make things a little easier to see. Sometimes it's hard to differentiate inside a bracket, and you forget to add the lambda in or something like that. Okay, so if you need to, you rewrite. Deriving with respect to x, we get 4y plus 2 lambda x. This 2 will come down out front. And everything else has no x's in it, so it stays constant. Deriving with respect to y. Okay. And deriving with respect to lambda, we will get our x squared, our y squared, and our minus 8 back. Now, critical points are found when our partial derivatives are each equal to 0. So we have a nice system of equations. We need to solve this to find our critical points. So we'll write them down again, nice and neat. Okay, what can we do? Well, I noticed the first two have x's and y's and some lambdas. What we might do is rearrange the first expression and say that 4y is equal to negative 2 lambda x. And then we can get y as a function, or as an expression in terms of lambda and x, and then take that and put that back in here. Okay, so you plug that into this expression, we'll get 4x plus 2 lambda negative 2 lambda x. Okay, so the 2's will cancel out. We'll be left with 4x minus lambda squared x is equal to 0. We can factor that a little bit. So now we have two options. Either x is 0, or 4 and lambda squared are the same, in which case lambda must be plus or minus 2. Okay, so each of these might give rise to their own different critical points. Or sometimes it happens that they all give you the same critical point, which is always fun when that happens. But each of them, in theory, gives rise to a different critical point, and so at the end we'll plug them all into our original function, 4xy, and see which one gives us the biggest value. Okay? So what can we do? Well, if we let x be equal to 0, okay, what's going to happen? Well, let's go back to this first equation. Okay, we'll have 2 lambda times 0. Well, that's just going to be 0. So 4y is equal to 0. Well, that means y is equal to 0. But x is already equal to 0. And if we look at the last equation here, we get 0 squared plus 0 squared minus 8 is equal to 0. That doesn't make any sense. Negative 8 equal to 0? Okay, so what does that mean? Well, we can't have x be equal to 0. Okay, it's just not going to work for us. Okay, so, if we can't have x be equal to 0, then that means lambda is either 2 or negative 2. Okay, seems reasonable. So, what do we get in those situations? Well, what can we do with our lambdas? Well, we could take them, plug them back in here, and understand a relationship between x and y a little bit better. So, let's say if lambda is equal to 2, okay, what does that first equation equal to? Well, we'll have 4y plus 2 lambda, but that's just going to be 4. X is equal to 0. And our second expression is going to be very similar. We'll have 4x plus 2 lambda, but 2 times 2 is 4. Y is equal to 0. You can divide both of these by 4, and what we've really got is x plus y is equal to 0. Okay? So what can we do with that? Well, that means that y must be negative x. So now we can take them and plug them into that last expression. And we say, okay, x squared plus y squared, but we know y squared is just negative x squared. Okay, bring the 8 over to the other side, we get x squared plus x squared is equal to 8. So 2x squared is equal to 8, x squared is 4, so x is plus or minus 2. And then y is just the opposite, so it would be minus or plus 2. So this gives us some interesting critical points to consider. Okay. 2, negative 2, or negative 2, 2. Okay. So those are some critical points. We'll just maybe put a circle around them. There's something to look into. Does one of those give us the biggest value for our function? Okay. The other possibility was maybe lambda is equal to negative 2. And that gives us a very similar situation, but now we'll have 4y minus 4x from that first equation, 4x minus 4y from the second equation. Either of these both work down to being x minus y. And that tells us x is equal to y this time. Plug into that last equation. We once again get 2x squared is equal to 8. We've seen this before, so x is plus or minus 2. But this time y is the same value. So either x is 2 and then y is 2, or x is negative 2 and y is negative 2. And that gives us 2 more critical points to work with. Okay? So to summarize, we have 4 possible critical points. Okay? And we want to maximize this function. So we want its maximum value. We don't actually technically care what the x and y are that do this, but let's work out what this maximum value is. So these are our xy's. What is 4xy for each of them? Okay, just take the x-coordinate and the y-coordinate that we found for our critical points, multiply them together. Here we'll have negative 16, another negative 16, 16 here, and a 16 there. So we can see the biggest value amongst all of these is 16. And by the theory of Lagrange multipliers, okay, that we've worked on, we know that if there is a maximum, it's got to be at a critical point. Okay, so the maximum value must be 16. And that's our final answer.